Hi, this is an explanation why do we need nonlinear activations functions in neural networks in less than 2 minutes. Lecimy z tematem. Let's start by defining the layer function f. Function f takes input x, multiplies it by the weights matrix and adds a bias vector. For now, it does not have an activation function. So, the first layer multiplies input x by matrix w1 and adds a bias vector b1. Analogous behavior for the layer 2. Now, let's define network function. The network has n layers and gets x as an input, and it inputs x on the first layer, and the output of the first layer inputs on the second layer, and so on. We can expand the equation for the second layer output. Note that there is matrix x multiplied by a multiplication of weights from the first and second layer, and there is an addition of three terms. Weights of layer 2 multiplied by the bias of layer 1 and bias of layer 2. Let's create helper variables w3 and b3. Using them, we can define the second layer output as an input multiplied by w3 and added b3. That's the definition of a layer, not a network. It turns out that weight matrices multiplied each other, and by doing so, they collapse into one layer. Now we don't have a network and only one layer. Now let us create a nonlinear activation function. We modify the layer function by inputting the results of the old layer to the nonlinear activation function. Expansion of the second layer's equation cannot proceed further because you can take arguments out of the function only on the condition it is linear. You can't do it with nonlinear functions, so weight matrices cannot collapse into each other. We preserve the identity of the layers. We have a neural network instead of just one layer. Basically, without nonlinear activation functions, we wouldn't have neural networks, we would just have one layer, one extremely big and non-efficient layer. So this is why we need nonlinear activation functions. Thank you for watching. Please consider leaving a like and subscribe, and we see each other in the next episode.